We are starting the second part of the chemical equilibrium based essential and important concepts. And this is the very important part of the chapter itself is Le Chatelier principle. And if you look at the Le Chatelier principle, it's very, very important. And it's really what it's all about is in a dynamic equilibrium, chemical equilibrium, if there is an external condition is acting on the dynamic equilibrium, the chemical equilibrium, the dynamic chemical equilibrium will adjust itself by shifting to the side to offset this introduced external condition. Those conditions can be pressure, change in pressure, volume, concentration, temperature. So, and this is all about the shift to offset the external condition acting upon the dynamic chemical equilibrium. Let's look one of the examples here. We have this reaction here. All of those are gases, and it's an endothermic because the heat here is at the left side. And it's asking what will happen, the shift of the equilibrium, if we add more methane gas. So methane is in the right side, so you put extra methane on this. So the left side, the reactant side, will be more stressed out, so it has to shift to the right. Now, if you add another reactant, H2S, if you add H2S to this, well, then H2S, the reactant side will be large. Will be more stressed, so it will go and release this stress by going to the right. So if you add one of the reactants, the shift will be to the product side, to the right. Now, if you look at this, this is the reaction here. Now we are trying to add now product. If you add the carbon disulfide products, well, this side will be more stressed out. The product side will be more stressed out. The shift will be which way? Will be to the left. Sorry, will be to the left. So shift adding hydrogen. That's another product. If you add it, the product side will be more stressed, and the shift will be to the left as well. Removing one of the reactant, if you remove this one here, so this side will be least amount and will be least stress, but the product side will be more, correct? And the shift will be to the left, to the left. And removing H2S, if you remove the same thing here, if you remove H2S, the whole thing will be the shift will be to the left. If you remove one of the products, will be to the right. If you remove carbon disulfide or you remove the hydrogen, will be the shift to the right. So this is straightforward. Now, when we come to the temperature a little bit, we have to watch temperature and the pressure and the volume, then we have to watch a little bit more. So the reaction, the concentration changing, adding reactants or removing reactants, adding products or removing products, that's straightforward. But now we have to watch for the heat. Again, this is an endothermic reaction, the heat at the left, at the reactant side. If you add heat, the heat will add itself to the side where it's to begin with. It's at the left, so the heat will be adding itself to the left. So the left will be more stressed out, so the shift will be to the right. Perfect. If you cool the system, means you get the heat out of your way, remove the heat. So then the right side will be more stressed out because the left side is losing one of its components, if you wish. So the heat can be as one of the components, like a reactant. So therefore, the removing the heat will be what? Shifting to the left. Now, the effect of change in pressure. So if you increase the pressure or decrease the pressure, it will depend on the number of moles of the reactants and the products. Here we have 4 moles. Let's look at the products. 4 and 1. This is 5. So the products had 5 moles. The reactants have 2, and understood nitrogen is 1 here. So 3. The reactants are 3. So when you increase the pressure, the shift will be towards the least number of moles. So it will be increasing the pressure. Increasing the pressure will lead to the least number of moles, which is 3 is the moles, which is the reactant side. It will go to the reactant side, correct? So it will go to the reactant side. Now, decreasing the pressure, if you decrease the pressure, it will shift to the most. Here is, we said, if you increase the pressure to the least number of moles, and here we have to the most number of moles. So decreasing the pressure, the number of moles of reactants, it will go to the most number of, and it will be to the number of, decreasing the pressure, it will go to the most, which will be to the left. Where is the most? The most are number 5. That's, the number of moles, the reactant side. So 5, and if you go there, 5 moles, and it will go to the, will shift to the product side, correct? It will shift to the product side. So let me repeat it again. If we have increasing the pressure, we will go, the shift will be least number of moles, least, L-A-E-S-T. If the pressure decrease, the shift will be to the most number of moles. So to the most number of moles. This is very important, very, very important. If I increase the pressure, the shift will be to the side with the least number of moles. And if I decrease the pressure, it will go to the most number of pressure, of moles, sorry. So the volume is quite the opposite, because it follows the Boyles Law. So if I increase the volume, meaning the pressure will go down. If I decrease the volume, the pressure will go up. So it's just quite the opposite. Increasing the volume, meaning what? The pressure will go. So it's always in direct proportion, Boyles Law. So remember this of Boyles Law? Increasing the volume, meaning decreasing the pressure. So it will go to the most number of moles. The volume is connected to the pressure. It's the same thing. You can visualize this as a Boyles Law. If I increase the volume, increase means I'm decreasing the pressure, and the shift will be to the most number of moles, correct? So, and the opposite, if I decrease here, if I decrease the volume, the pressure will be high, and the shift will be to the least number of moles. So that's what all this slide is telling us. So it's Boyles Law, and this always, the volume, as Boyles stated, is always indirect proportional to its pressure. So that's what it really says in the previous slide. The effect of adding a catalyst. The catalyst has no effect on the chemical equilibrium. The catalyst is always decreasing, speeding up the reaction, the rate of the reaction, by decreasing the activation energy, correct? But it does not have to do anything with the chemical equilibrium. Let's go and look at the sum of the reaction here. Here we have 1 mole. Here we have 2 moles. So the number of moles of the reactants are 3 moles. So look at this, and the number of the product number of mole is 1. So it's 1, correct? Now you can increase the volume or decrease the pressure, or vice versa, and then you can see where it will go. So let's go here and look. Number of moles. So carbon monoxide gas is added. You add one of the reactant, the shift will be to the right. That's correct. Temperature, this is minus, negative. This is an exothermic, so the heat will be in the right side. This is the heat here, will be added here on the right side, correct? So if you increase the temperature, the right side will be more stressed, so there will be to the left, will be to the left. And if you increase the pressure, now look at this, we are increasing the pressure, and if you increase the pressure, it will go to the side with the least number of mole. The least number of mole is the product side, correct? One more the product side, so it will be to the product side. Perfect, good. Now if we remove hydrogen from the system, we have to go up and look what will happen if we remove hydrogen. So this side will be, the product side will be higher. So if you remove one of the reactants, shift will be to the reactant side to compensate for the loss of the reactant side. So let's see here, this shift will be to the left, correct. If you add catalyst, no effect. What will happen if the total volume is increased? Increasing, now we have increased the volume, meaning what? The pressure is decreased. So you are shifting towards the number of moles. Least or most? Well, look at this, your decrease will be towards the most. So the most are, let's go back, the most are 3 to the left side, correct? Will be to the left side, that's correct, to the left side. Now look at the trick now. We are increasing the volume or decreasing, what, the same thing here. Increasing the volume or decreasing the pressure, it's the same thing, correct? It will go again to the left, so it will go to the left. So that's what it says, so we have to watch for the Boyles law here. Now, we'll inspect the effect of changes on chemical equilibrium. We can do it through the kinetic, or we can do it through the reaction quotient. Kinetic, straightforward. So what you have this Haber-Bosch procedure to produce ammonia. So now if you look at this reaction here, and then you come up with the rate of forward reaction. Rate of forward reaction is the rate constant of the forward reaction multiplied by the reactants, which is in this case nitrogen and hydrogen, and this is just the order, reaction order. M and N is reaction order, not the number of moles, no, reaction orders, that's kinetics. So now if you reverse this reaction, make it, this is the forward, this goes this way, forward. Now if you go backwards, then the ammonia will be your reactants and the nitrogen and hydrogen will be your product. So the reverse will be R reversed, the constant of the reverse rate constant of the reverse reaction multiplied by the reactants, this time is ammonia, and then this reaction order. So, and at the equilibrium both rates are equal, so both at the equilibrium both rates are equal. So you set them up together and then you count up you can inspect when they are together what you get. So if you stress one side on the other side, then that will affect the values of the reactants concentration or the product concentration. For example, when the chemical equilibrium is stressed by adding one of the reactants, so either nitrogen or hydrogen, you add, this will increase the concentration of the reactant to lead to increase of the reactant's concentration. Therefore, the rate of the forward reaction will increase, and it will be greater, the forward. So if you add one of the reactants to the main reaction, this is our main reaction here, you add one of the reactants, that will lead to the forward rate of the reaction will be higher than reverse. Now, with the same token, you can reverse it. If you add more from the products, then you can get the reverse higher than the forward. So as here, this is the reverse is higher than the forward, correct? So now you can see with all this inspection of the kinetics, you can see how the stress affecting the chemical equilibrium shift. So we can do this one here with the just chemical equilibrium quotient, correct? The chemical equilibrium, the reaction quotient QC at the equilibrium will go to will equal to the chemical equilibrium constant Kc. So chemical reaction quotient, chemical reaction constant. So products, correct, over the reactants, and those are number of moles. Those are number of moles. Now they are equal, correct? Now if the reactants, if you add one of the reactants, if we add one of the reactants, this side will be very high, correct? So that will lead Kc to be very, very small, and Kc and QC will be less. On the other, this is what we have here. If you add one of the products, then you will have QC and Kc will increase. So we can expect this type of the shift by looking at the Kc and QC at the equilibrium. So that's what you have when you add one of the one of the products, or so then you have QC, the QC increase, and the shift will be towards the adding the products. So QC will be greater than Kc, and the reaction will go to the reactant side, favors the reactant side. So on the other side, if you go back here, it favors if you add more of this. So QC will be less than Kc. So Kc is larger, so it will go to the product side. So just inspection of how to do this. Now we'll introduce ourselves the partial pressure of the reactants and the products. So in order to connect the chemical equilibrium with the partial pressure, we have to go to through the ideal gas equation, PV equal nRT. That's well known. If you divide the volume by both sides, so you eliminate the volume from the left side, then it appears here. N over V, number of moles over the volume is equal what? Equal the molarity. Equal number of moles over the volume, that's molarity, correct? So the molarity is N over V, which is equal then the partial pressure divided by RT, gas constant, multiplied by temperature in Kelvin. So if we consider our reaction with using just not the molar concentrations, but we use the partial pressures of the reactants and the products, then the partial pressure of the ammonia squared divided by the product of the reactants partial pressure. Here note this is cubed for hydrogen, and this will be our Kp, this chemical equilibrium constant, using partial pressure of the reactants and the products, correct? So now if we can expect on this, if we increase, let's expect in this. We know this, the reaction, the chemical reaction is in the equation here somewhere. This is what we started with, the Haber-Bosch reaction to produce ammonia, correct? Now, if we say that we are increasing, correct? We are increasing the partial pressure of the reactants and the product by a factor of 2, correct? So 2, and each reactant and product by a factor of 2. We add of that, so then you have open this 2, 4, there will be 4 here. And here cube, that's 8, multiplied by 2, that's 16. So if you increase the partial pressure of the reactants and products, you will end up that's QP is less than Kp, is 1/4. This will be 1/4 QP, and therefore Kp is greater than QP. So that's when you increase the partial pressure. When you decrease, decreasing the volume in turns meaning increasing the pressure. That's Boyles law, correct? And when we increase decrease the volume, increase the pressure, the shift will be increasing the pressure. Will go to the least number of moles. The least number here is 2. Here is 1 and 3, 4. It will go to the right, to the product side, correct? With the least number of moles is 2 moles here, and the reactants are 4 moles. We'll come back to the effect of catalyst. Well, the catalyst has really no effect on the chemical equilibrium. What it really does, as we will see from the figure here, it really affects the rate of the rate of the reverse reaction as well as the rate of the forward reaction in the same magnitude. So let's look at this curve, this blue curve here. This is without a catalyst. You can see without the catalyst, the activation energy is large. And from here, you can see the activation energy from here all the way to here without the catalyst, correct? If you use the catalyst, then you are reducing this one here. So this is the green one here. You're reducing it, activation energy, you're using the catalyst. But the rates are really declining, correct, with the same magnitude. So here this is the same magnitude for without the catalyst, correct, and here it is, and with the catalyst is really here it is. So here it is. This is with the catalyst, and you see you are really moving using a catalyst. You are moving the rate of forward reaction and the rate of the reverse reaction at the same magnitude. So there will be no change. The net change is really zero. The same. The rates are equal, still equal. Does not really change. So therefore, we say the catalyst is really just minimizing or decreasing the activation energy, so that the reaction will progress faster. But it does not really affect the total net change of the reverse versus the forward, and therefore has nothing to do with the chemical equilibrium. Effect of temperature, well, as you see, if you have seen of the reaction here, you can inspect this in this here. This is an Haber-Bosch producing ammonia procedure, is an exothermic reaction, and we can expect it this way. Here we can having the rate of the forward reaction equal the rate. This is reverse reaction. This is the reverse of the reaction. This is the forward rate of the reaction. They are equal. Put them together, and the rate of the forward, the constant of the forward rate of reaction divided by the rate constant of the reverse rate of reaction will be looking like this here. And then you can expect how the Kc is connected to both of those two. So now, if you add heat, whenever you have temperature, if you add heat here, if you add heat, the heat will add itself to whatever the reaction is, exothermic or endothermic. So it will add. If I add heat, it will add this to the right side. The right side will be, the product side will be more stress, and will be shift towards the reactant side. And the same token, if I pull out the heat, cooling out the system, I'm removing the heat from the product side. Therefore, now the stress will be on the stress will be on the reactant side, because the right side is, the product side had lost it's one of its components. So the shift will be, if I cool the system here, the shift will be towards the product side. Okay, now to the last topic of the module is chemical equilibrium calculations. It's a very interesting calculation. It's not really difficult. We'll be using the ICE, not ICE. It's not stand for ice of solid H2O. No, ICE table. I stand for initial concentration, C, change in the concentration, and E, concentration at equilibrium. So I, initial, C, change, and E is at equilibrium. So let's look at one of the example here. We have this equilibrium here. nitrogen monoxide with oxygen give you the brown gas, dioxide, nitrogen dioxide, brown gas. NO is no color, but then when you add oxygen to it, it turns brown gas of nitrogen dioxide. Now, we can, if we have the equilibrium concentration, this is for NO2, this is for oxygen equilibrium, correct? And this is for NO, monoxide, nitrogen monoxide. Just plug them in because they are at equilibrium, so we don't have to do IC here with table. So we put them in, and remember always watch out for the 2 here, the number of moles. Here is 1 understood, not written. So just plug everything in, and there will be the NO2, the product over the products of the reactants concentration with concentration of the number of moles here, and you get this value. This is straightforward because it's given to us, the concentration at the equilibrium. But most of the time on this type of calculation, what's really asked is the concentration at equilibrium. We call it unknown X, and that's what we most of the time calculate. Now, let's look at this reaction now. What I did, I divide both side reactant by 4, and now I have what? I have this equation because it came from this. So I divide this reaction here by 4 to get this, a new problem. So we have to solve this Kc. You have to find Kc. Well, it's not really difficult. We do have the same. We will use the same amount here, correct? We'll use the same amount of equilibrium at concentration, equilibrium concentration. So we plug just we watch for the power. This is half. This is 1/4. This is half. So plug all this initial concentration with their corresponding number of moles, fractional number of moles, and you will get the value 1.87. So dividing the equation, the original equation by 4, lead a reduction Kc from 12.1 to 1.87. So now let's look at this. We'll find the equilibrium constant. Find the equilibrium constant. It's given to us the concentration A and B, correct? A, B, and A2D, and they are at the initial concentration for both is 0.3, correct? Before they are mixed, but when they are equilibrium reached, the equilibrium of A2D is 0.2 molar. So use the IC table for your calculation. Well, if you look like this is solid, so there will be discard. This is solid, will be discard. So this is not part of our consideration for Kc because they are solid. So really Kc is the products over the reactants, and we have to watch for the 2 here, become power 2. So it's 0.2 divided by 0.5 square, 0.8. Okay. Now, let's go back here. Find the equilibrium constant Kc of the following initial. Yes. So this is just the 0.8 when we have the Kc. So we find the equilibrium constant, the initial concentration is this. But this is not the whole story. So we start with 0.3 of AB, correct? And AD is, the initial is 0.3 for both. Now, if you look at the whole thing, this one here at the equilibrium is 0.2. So then the change here is this one here. That's the change because this is the if you look at this, you go back, AD. So this one here is, yeah, so this is AD here, and here will be, yes, you add them up, correct? You have to add them up, and it will be 0.5, and when you put them together, then you can get the the amount. Let's look at another example. Maybe this example is not obvious, but let's look at the one of the examples here. Yeah, let's put the one of the examples. This is 0.5 from the IC. From the IC is 0.5. You add this one up, subtract those 0.2, and you get the whole thing here. But let's look at this one maybe more relevant to ours. So 0.5 mole of the reactants. This is the liters, so you divide this by this to get the molarity, correct, of NO2. And this is here what we have here. This is what we have here, correct? That's what we have here. Then this is the products at the beginning, 0, 0, correct? 0, 0. Now look at the whole thing. The change is this one here. This is the reactant minus 2x, correct? Minus 2x. Here is the product plus 2x, and here's the product plus x. The 2 is, we have to consider always the 2 here with us. So 0.250. This is the from the initial one. We divided 0.5 divided by 2 gives us 0.25. So now what we'll do, you plug your Kc value. The Kc value is given to us, is here. Kc value is 1.10 10 to minus 5. Is the products over the reactants, correct? And you said the products, we have two products here, one oxygen and one nitrogen monoxide. And here we use this, when you add them up, that's what you use here. And we use all this at the equilibrium. The Kc value, so will be this when we use the assumption for the reaction. So our assumption is 2x is too small compared with 0.25 because Kc is so tiny. Kc is so tiny, and therefore 0.25 molar is greater than 2x, so the 2x will be out. So we took the 2x here out. So now set up the whole thing here together. When you set up the whole together, 4x cubed and all this here, correct, square, this is cubed because 2x. See here, this is 2x and x. If you multiply them, that's 2x, 2x, correct, and then the power of the number of moles. So just multiply the whole thing, and then you end up with solving for x. When you solve for the x, you get the x value is this one here. Now you go back and just set up your. So what is your at the equilibrium? 0.250 minus 2x will be your NO2. The NO will be 2x and the oxygen will be x. So going like this here. So 0.25 minus 2x, that's the NO. NO2, NO is 2x, will be this, and this will be this, and then the oxygen is just, the oxygen will be equal your x. That's your x, the oxygen. So this is the oxygen here. Another example. Again, we did not solve quadratic equation here. We'll do one example quadratic equation at the end, but we did just assumptions. Make, the assumption is we assume that when the Kc is very small, then we can get rid of the 2x in this example. Let's look at this. Calculation of equilibrium concentration using initial concentration in equilibrium constant. So the Kc is given to us at 900 K. The initial concentration is given to us. This is 1 for CO2 is this, correct? For hydrogen is this, okay? And for the initial carbon monoxide is not produced and the H2O is not produced. So let's go here. We'll say minus x for the reactants, plus x there will be produced, plus x there will be produced. So produced plus consumed minus. Add them up, then you get this one here. Add those up, you get this one here, and this one here 0 is x, the 0x. Set up your Kc. Kc will be the product over the reactants. This is the product here, and this is the reactants here, and you replace them with the values. Replace them with these values now. So replace them with these values, will be x multiplied by x over 0.10 minus x 0.1. So you have Kc is 0.64. We can take both side square roots for both sides. So you get something looking like this and work it out, and you get the x is 0.0444. So just simple algebra here, and you can work it out and get the x. So then you go back and look to the values here again. The reactants, hydrogen carbon dioxide, is 0.100 minus x, and the product is xx. So the reactants is the reactants are 0.10 minus x, and this is the value, and this is the value of the reactants, both of them the same reaction. The products are x, which is 0.0444. So now let's look at the example number 6. For the system, if we start with 0.10 mole of hydrogen and iodine, and 0.96 mole for HI. So HI is our reactant, and hydrogen, all of them gases, correct? And iodine are our what? Our product. So it looks like hydrogen iodide gas will be decomposing, or hydrochloric iodide will be decomposing to get hydrogen and iodine gases. So initial concentration is given to us. The initial concentration of HI is 0.96 molar. Okay, the initial concentration of the product is 0.10 both. So then you set up, watch out for the 2 here, minus 2x, here plus x, here plus x, correct? Because it's 1. There's no 2 or 3. So you add them up here, add those up, you will end up with this. Add those up, you end up with this. Add those up, you end up with this. Here it is. Now, the problem here, it was given to us the Kc value, but really we don't know where the action would go, because we have the initial concentration of all the reactant and product at the same time. So we don't know where, when in this case we got all the initial concentration of both reactants and products, we don't know where the reaction will go. Shift left or shift right, we don't know. So which will be more favorable? The right side, product side, or the left is the reactant side? Well, let's see here. We have to get our QC and compare it with our value of Kc, which is here. Look at this here, Kc. This is our Kc, 0.16. So, and put all those initial concentration, as you see, and it turns out the Kc here, look at this. Kc came out to be point. So I use this. This is the reactant. This is the product here. This is another product. So products over the reactants. Put the initial concentration. QC came to be less than Kc. In this case, what will mean? Means Kc is greater, so it has to favor what? The product side, correct? It has to be product side. So Kc is 0.06, and it's really shifting to, it favors the product side. So Kc is, we just put the product side here. Here it is. So we have, let me go back. So if you look at this, so we have, it's here the product side. So just plug in all this here. We are plugging these numbers here. 0.906 minus 6, 0.01 plus x, 0.01 plus x. So do the same math here. The products over the reactants. This is product, this is product, this is the reactant. Well, then if you look at the whole thing, you multiply and you get up, something like quadratic equation. Take the square root of both sides. you will end up having this equation, correct? So then do your multiplication here. So when you do your multiplication, you will end up just solving for x, and x will be 0.00846. So hydrogen and iodine, those are our products, and those are the initial concentration plus x, and the hydrochloric hydrochloric acid gas is minus 2x. So the initial concentration minus 2x, which is 0.00846, will be came up to be equal this amount. So you can see the difference between those reactants has a lot. The concentration of the reactants is large. Now 7 is at 650 centigrade Celsius, the reaction below has Kc value of this. This is very important. If we have 2 moles of both hydrogen, carbon dioxide are placed in 4 liters, remember, take those moles, you divide them by liter to get the initial concentration, correct? Mole per liter. What will be the equilibrium concentration of all 4 gases? What will be? That's equilibrium concentration. That's our x. Always we are acting for x. You can see. So well, you have make your table here. Here is the table. The concentration, initial concentration is, as I said, take the moles, divide by 4. Correct. This is your hydrogen and CO2. Your what? Your reactants. So this is your reactants here. Okay, will be 0.5 odd, will be 0.5 both. So the products we don't know, 0, 0 at the beginning, initial 0, 0. The reactants is 0.5, 0.5. Minus x, and here is produced plus x plus x. Remember, minus x is consumed, minus x, the minus means consumed. And the reaction, there is no 2x or 3x, because you go back and look, all of this 1 to 1 to 1 to 1 more ratio. All the ratios are 1 to 1 to 1 more ratio. That's good. So now we have to use this. We know the value of Kc, which is this, correct? We can even verify this Kc is, here it is. That's the Kc value. So let's go back, and we will be using this here. Those are my reactants, and those are my products. So the product is x. So it will be x, 2x's, x squared, divided by the 0.50 minus x, 0.50x will equal the Kc value. Then you get something looking like this here. So both sides, you can take the square root of both sides. And then from doing this, is a simple calculation manipulation, you get x equal 0.239. So the products, which is XX, carbon monoxide and H2O, equal the x value. The reactants will be 0.500 minus x will be 0.261. So this is. Now, the last example here, will be looking at the maybe we'll be looking at the chemical, getting our x, but using the quadratic equation. That would be interesting to look. We kept it until the last because it's very hard during the exam to use the quadratic equation. It will eat up the student time. So we use all the time the assumption type of calculation manipulation rather than the quadratic. But for homework or worksheets at home, you can use the quadratic equation at your convenience. So, but let's look at this. Carbonyl bromide, this one here, is a product. Can be found by reaction of carbon monoxide, that's the reactant, with the bromine gas. A mixture of 0.4 mole of CO, correct? So CO is 0.4 mole, divided by the flask is 5, correct? That's the volume. So by this, it gives you the concentration of the carbon monoxide reactant. And the other one, the bromine gas, is 0.3 mole, correct? Divided by the liter give you the molarity of your reactant bromine gas. The product on the other side, the product is calculate the equilibrium concentration, which is X. That's what it says, X. So this is, we started with 0.2. This is our product divided by 5.00 liter will give you 2.004. So now we want to see the reaction. Is it to the product side? Will be okay, or have no problem. But if the reaction goes to the other side, Kc is here. Look at the Kc value. We have to compare. Every time we have to, just to check if we are on the right track. So now let's check. The Q here is the product. One product here we have. All this 1:1 mole ratio. The product over the reactants. And we set up all those values here. All those values are used. And it looks like the QC is 0.833, but the KC is 0.680. So QC is greater than the KC, which is this value here, KC. So it means this reaction here, it favors what? Favors the reactants, correct? I mean, it favors the reactants. So it's really, this one will be our reactant in the table, ICE, and those will be our what? Our products. Although it's written this, but the reaction is, by just comparing the numbers here, will favor the product. So the negative, the consumed, is our, in the reaction product, but here in the IC is negative, because the shift of the chemical reaction to the left, more reactants produced than the product. So, and here is produced, will be positive. The bromine is reactant, but it's really produced. And the carbon monoxide is produced plus X. So you watch out for always testing those two values. If it's Kc greater, then you don't have to worry. The reactants will be minus, the products will be plus. But in this case, if you watch, the Kc is much larger than, I mean, QC is larger than Kc, then you have to shift the sign, flip the sign. The reaction will be product, the product will be sign. So the consumed is COBr, 2-carbonyl bromide, and the produced is your bromine gas and CO. So there will be minus, and this is the initial concentration from this. Those initial concentration are here now. Look at them. And then at the equilibrium, we have this. We use it. We'll be using this. We apply the value Kc. Kc is the product, as we have before, product over the reactants. And just we plug those numbers, correct? This is 0.004 minus X. And this is for the 0.08 for carbon monoxide, 0.06 minus plus X for the bromine gas. Now, here is we have to apply for the quadratic equation. So solve the whole thing, you will end up with the equation looking like this. We are not doing any assumption. We did not assume anything. We could have solved the whole thing here easier by doing some assumption, correct? So we can see that's the 0.08 greater than X, much greater than 0.8, so we can get the X's out here. But we did not do that. We want to see how to now solve the problem with more details. So using the quadratic. In the quadratic equation, you have this quadratic equation. Your A is this amount here. This is your A, and this is what's here given. The B is, this is the B here, correct? And the C with the negative. This is your C value with the negative. So this is the C value. This is with the negative. That's your C value. This is your B value. This is your A value. Now, put them together, you get two values. One negative, one positive. Ignore the negative. We take what? The positive value, which is this value. This is the positive value, and we adopting it, and that's what we need. And then you just plug in the product here. I mean 0.004 minus X, correct? and here 0.06 plus x and 0.08. So just plug in those together here. Here is minus x, here's plus x, 0.08, and here plus x with the initial concentration, and your values will be looking like this. Thank you very much for listening. And this will end of the chapter 13.